Welcome to the Insight Engine podcast. This episode is brought to you by Royal Research, an organization dedicated to accelerating breakthroughs in the applied sciences. Every autonomous machine operates under a severe computational paradox. To successfully navigate a single turn, a self-driving car must process millions of LiDAR data points, calculate the exact kinematics of its wheels, and execute steering commands simultaneously. Standardizing this highly complex parallel behavior across diverse physical platforms, from four-wheeled cars to aerial drones, requires a unifying software architecture. Monolithic software design poses a significant risk to robotics. When sensors and actuators are tied together with direct code dependencies, the system becomes fragile, breaking the moment a single hardware component is changed or upgraded. The Robot Operating System, or ROS, provides the industry's structural solution to this software fragility. Efficiently managing an autonomous robot requires solving a massive distributed routing problem, a challenge that monolithic code cannot survive. To understand ROS, we must first address a common professional misconception. Despite the name, ROS is not an actual operating system. Robots typically run on a host operating system like Linux, which manages foundational requirements like memory allocation and CPU scheduling. ROS is middleware, a highly structured communication layer that sits directly above the host OS. This layer acts as a unified network framework, capable of routing data packets between independent processes across a heterogeneous compute cluster. This architecture decouples complex software by breaking the system down into a distributed network of independent modules, rather than a single massive application. By transforming the robot from a single vulnerable computer into a resilient network of microservices, ROS prevents local code failures from causing total system collapse. We can build the ROS architecture from its fundamental building block, the node. A node is a discrete, single-purpose computation process running within the robot. This specific node might spend its entire life cycle ingesting and filtering a raw camera feed, isolated from other tasks. We can then introduce a second node dedicated to a different mechanical function, such as wheel motor actuation. These units remain strictly isolated. By design, the camera node operates with zero awareness that the motor control node even exists. This modularity allows developers to swap, upgrade, or debug individual hardware components without affecting the rest of the machine. If nodes are strictly isolated, we must find a way for them to communicate without creating the direct code dependencies that ruin monolithic systems. ROS solves this through a publish and subscribe paradigm, which allows for asynchronous data sharing. Communication happens through topics, dedicated, named data streams where messages are routed through the system. When a sensor node broadcasts its data into a topic, it does so without needing to know which other nodes are listening. An actuator node simply listens to the topic conduit and pulls the exact data it needs to function. Unlike traditional direct coding, topics allow for multiple publishers and multiple subscribers on a single data stream without interference. This creates a scalable architecture, where adding a new sensor, like a LiDAR unit, requires simply plugging a new node into the existing network, rather than rebuilding the system's logic. While topics are ideal for continuous sensor data, robots also require the ability to execute specific synchronous commands. For these one-off tasks, ORS uses services and actions, models designed for request and response communication. A service handles immediate queries, such as a master node checking the battery status and waiting for a specific response. An action handles tasks that take time, such as commanding a robotic arm to execute a complex movement sequence while providing progress updates. Combining these nodes, topics, and services creates a standardized operational framework. This commonality enables developers worldwide to contribute to a shared, high-performance codebase. Because the architecture is standardized, engineers no longer have to build foundational robotics algorithms from scratch. The navigation stack is a primary example, a community library that handles path planning, localization, and obstacle avoidance. For motion planning and kinematic control of robotic arms, developers rely on the industry-standard tool, MoveIt. These complex community libraries exist as pre-packaged nodes that can be integrated into any developer's custom node graph. This open-source ecosystem accelerates the entire industry, allowing researchers to share foundational capabilities and focus entirely on novel applications. Moving these decentralized systems into real-world production reveals the limitations of the original framework. ROS1's primary vulnerability was an inability to guarantee strict real-time execution. In complex environments, it struggled with data packet latency. Deterministic performance is essential for safety. If a self-driving car reacts to a hazard, a delayed command can lead to system failure. ROS1 also faced security challenges, as it was a research-focused framework that lacked built-in protections for distributed systems. This created enterprise risks, where unprotected data packets could potentially be intercepted or manipulated as they traveled across the network graph. While ROS1 was a triumph for academic prototyping, its architecture could not meet the stringent demands of commercial autonomy. ROS2 represents a necessary evolution, engineered to upgrade the framework into a resilient enterprise standard. ROS2 redesigns the middleware layer to support the real-time capabilities required for industrial applications. Enhanced security protocols are now integrated directly into the architecture, using encryption to protect data as it moves between nodes. Despite these upgrades, improved documentation and tools have simplified the learning curve for engineers adopting the new standard. The core philosophy, strict modularity, isolated nodes, and asynchronous topics, remains the center of this next-generation system. ROS serves as the unifying language of modern robotics, accelerating the timeline toward true autonomy and architecting the future of intelligent machines.